So I'm Stephen Giacalone. I'm a NSF postdoc fellow at Caltech, but today I'm actually going to be talking about some research I did in grad school with my advisor, Courtney Dressing, back at Berkeley. So the title kind of gives it away, but I'm going to tell you how we got there and why I think it's a little bit interesting for the folks here. Okay, so as Lauren nicely showed us before, we're roughly 30 years into exoplanet exploration, and to demonstrate the types of stars that we found exoplanets around, I'm going to play this little animation that shows just a histogram of stellar effective temperature of exoplanet hosts as a function of time. And we'll see we get a little bump here with Kepler, a little bump with K2, and then a smaller bump at the end with TESS. So the thing I want you to take away from this histogram is that a vast majority of the types of planets that we found orbit stars that are roughly like the sun, FGK-type stars with effective temperatures between roughly 4,000 Kelvin and about 6,500 Kelvin. This isn't a coincidence. Kepler mostly looked for planets around sun-like stars, and radio velocity surveys tend to avoid these early type stars like A-type stars because they just spin too rapidly to get PRVs for. So this is really good, and we've learned a lot of cool statistics from this, but I would argue that we're missing a piece of the puzzle about the inner parts of disks, and specifically how that relates to planet formation, just based on this sample alone. So I would argue that we really want to extend into this region of early F-type and A-type stars to get a better picture of planet formation. Okay, quick recap of some of the points that Jesse brought up on Monday. So two trends that I'm going to come back to a few times in this talk. One is the distribution of planets in period space, and specifically this fact, as Eve talked about yesterday as well, that after about 10 days, you have a flat occurrence rate, roughly flat occurrence rate of super-Earths and sub-Neptunes. But as soon as you drop below 10 days, things start to decrease as you move towards the star. The second thing I want to bring up is this overall trend where as you move to hotter stars, or equivalently more massive stars, you have an overall drop-off in the occurrence rates of planets of pretty much all sizes, except for maybe the Jupiters. Okay, so keep the period thing in mind. I'm going to focus on this mass thing first. So there are a couple of reasons why we might see this change in overall occurrence rate as you move to more massive stars. I'm just going to sort of ramble through a couple of them to demonstrate how many processes are really going on here. So one is disks. So as you go to more massive stars, you have more massive disks that also dissipate more quickly. We also know that as you go to hotter stars, your dust sublimates further out. So there's a bunch of stuff happening in disks that could affect planet formation. Companion rates. We know that more massive stars more frequently have really massive super Jupiters, essentially, from direct imaging surveys. And we also know that these more massive disks tend to be more extended and have more gaps that are probably related to those planets. And then last thing is that more massive stars tend to have stellar companions more frequently. And so as Lauren showed, these stellar companions may be influencing planet formation in a way that giant planets don't. And then the last thing of these gradual changes is just age, right? More massive stars age more quickly, which means that any population of planets that you observe around massive stars is going to be on average younger than anything around sun-like stars. And so processes that take billions of years to unfold around sun-like stars might not be happening around this population. Again, also as Faye showed nicely, these resonant chains being an example. All right, so those are gradual changes that we sort of expect across all spectral types. But there's also a pretty sharp change that happens right around the 6,500 Kelvin temperature, which is where our limit of planet demographics really stops. And that is stellar structure changes pretty drastically. So as soon as you cross the Kraft break, the 6250 Kelvin, you go from having convective exteriors to having radiative exteriors, and eventually having fully radiative stars. And it turns out that this can change a lot about how your star interacts with your disk and with the planets. So one thing is tides. There's pretty compelling evidence that the dissipation of tides in the star changes drastically as you go from this switch in the stellar structure, which could affect things like orbital migration. Magnetic interactions, as we saw yesterday with Arturo's talk, these more massive stars have weaker magnetic fields, and so your truncation radius moves inward. And eventually, as you keep going up to hotter and hotter stars, you might stop getting magnetospheric truncation altogether, and you might just get boundary layer accretion. And the last thing is radiation environment. So if a star has a weaker magnetic field, it probably emits less EUV radiation, and so maybe photoevaporation plays a weaker role for the sculpting of planets around these relatively massive stars. I say that with a caveat because there's some work that shows that near ultraviolet continuum emission may be able to sort of pick up the slack and photoevaporate planet atmospheres pretty efficiently as well. Okay, so let's go back to this cartoon This is definitely the worst version of the cartoon that we've seen this week. So I apologize for that. But our cartoon of the inner disk. So for a classical T-Tauri star, again, as Arturo talked about yesterday, the gas truncation and the dust sublimation are roughly at the same radius for the average star, right? They both happen at about 0.1 AU, roughly 10-day orbital period. And so if we want to figure out trends like why did you get this knee in the orbital period distribution, it's kind of hard to figure out around sun-like stars because the truncation happens at 10 days and the sublimation happens in 10 days. And so we don't know if planets are stopping because that's where the gas stops or if that's because where the dust stops. And so there have been a few different papers, a lot of which are by folks that are here, that sort of predict where planets should stop in the disk given these different radii. So it's hard to figure out for sun-like stars. But as we move to more massive Herbig AE stars, which become our A-type stars, we get a change in the inner disk that can let us sort of break this degeneracy. So specifically, again, as Arturo said, your truncation radius moves in, but your dust sublimation radius moves out. And so we have this really interesting opportunity to figure out where does the migration of planets actually stop based on these two radii. And so we can make a sort of prediction here. If planets care about the truncation radius as their innermost radius, then maybe this trend for a downward occurrence rate will level out or even turn around as you go to A-type stars. On the other hand, if it cares about where dust sublimates, if that's where they stop migrating, then it'll probably continue to decrease in this region, but then maybe you'll start seeing planets right when you pass the dust sublimation radius. So I set out to answer this question in grad school using TESS. So if you're not familiar with TESS, Jack might have an issue with this definition, but it's sort of like Kepler, but it's all sky. The simplest definition. So it looks for transiting planets across nearly the entire sky, and it doesn't have any preference for the type of star that it looks for planets around, which means that for the first time, we can really do a large uniform search for transiting planets around A-type stars. So we defined a sample of roughly 20,000 A-type stars, and we decided to search for planets between 2 and 8 times the size of Earth. We don't go quite down to Earth radius because these are big stars and those are shallow transits, so we don't really have that sensitivity. And then again, we limited our search to things with orbital periods less than 10 days, just because that's really what TESS was sensitive to at the time of this study, which I'll remind you is within the sublimation radius for these A-type stars. And I'll skip over the technical details, but the spoiler alert, you probably know from the intro, we didn't find any planets around these stars. So 20,000 stars, 0 planets with radii less than 8 Earth radii at orbital periods less than 10 days. So we can actually make some meaningful constraints on occurrence rate based on this. So here I'm showing a plot of occurrence rate as a function of stellar effective temperature for sub-Saturns, so 4 to 8 times the size of Earth, and sub-Neptunes, so 2 to 4 times the size of Earth. And these points are from a paper by Michelle Kunamoto in 2020. And so now I'll overlay our 3 sigma upper limits that we get based on our non-detection of any planets. And there they are. And so we see that there really seems to be a continuation of this trend for pretty much all planet sizes. That's as you go up in effective temperature, your planet occurrence rate goes down. All right, so now we have a question, right? We know that there aren't many planets in this region where there's no dust in the disk, right? So we're in this gas-only part of the disk. Thanks, Jack. And so we have a question of, are we seeing an effect that is due to these like overall gradual changes that you see with increasing stellar mass? Is that just the reason for this continued decline in occurrence rate? Or can we really tie it back to these sharp changes in the inner disk morphology, where the truncation radius goes in and the sublimation radius goes out? And the thing that we need to figure that out is, do planets start appearing where we think the dust sublimation radius is, right? If you start seeing planets after that, then it's probably telling you that, that's where the planets stop migrating. And it turns out we do. So I said that we didn't find any planets less than 10 days around our sample of stars, but we did find one planet at a 30-day orbit around a star with 8,500 Kelvin effective temperature. So this is a sub-Neptune. It's about 3.7 Earth radii. And again, this planet appeared right around where we think the dust should sublimate. And we actually got pretty lucky in even finding this planet because the star happened to be in a region of the sky that TESS observes a lot. So we were able to get a lot of transits. So we can't really say anything statistical about, like, do you start getting a pileup of planets here? Because we only have one planet. So it's plus or minus 100%. But I think it's compelling evidence that maybe you start seeing planets right around where the dust sublimates around these hot stars. Another interesting thing we could look at is the ratio of the frequency of sub-Neptunes to hot Jupiters as a function of stellar effective temperature. So it turns out hot Jupiters are pretty much, while they're intrinsically rare around all types of stars, you do find them around all types of stars, regardless of their effective temperature. So they're around M dwarfs, they're around sun-like stars, and they're around A stars. And so, again, these blue points are from Michelle Kunamoto's paper, and the green points are constraints on hot Jupiter occurrence rate from another paper by Michelle and her student. And so the shaded blue region here is showing the ratio of the frequency of sub-Neptunes to hot Jupiters. And you can see as you move to these hotter stars, the region becomes more narrow, which effectively means your small planets become rarer faster than hot Jupiters do as you move up in stellar effective temperature, which is probably telling us that these two types of planets have some different processes that are causing them to get to these inner regions of the disk. So one possibility is that the hot Jupiters just don't really care about the disk. They all get there via high eccentricity migration, so maybe they start out farther and then get scattered in after the disk dissipates. But another possibility, again, referring back to Arturo's talk, is that maybe the hot Jupiters can just plow through the dust wall and could just get really close to your star, whereas the small sub-Neptunes can, so they get stuck out by the dust sublimation front. And that's it. So I'll leave up my summary slide. If you want to check out the paper, you can scan the QR code. But I'm happy to take questions. And thank you.
Thank you very much, Steve. And this paper is open for questions. Yeah, let's start.
Thanks. So Mario Flock from MPA, great work. So this is something, I tell since 8 years, that you have actually to look, at the dust sublimation and actually the connected dead zone inner edge, right, which can actually block migrating planets very efficiently. Mm-hmm. So we would predict, I guess, the rise in occurrence rate for planets for A-type stars at, let's say, at around 100-day orbital period. I mean, is there anything in the future which would, investigate this sort of regime where we could actually prove that,
You said at 100 AU?
No, 100 orbital days, so around 0.3,
okay.
0.4 AU, I would expect a rise around the A-type star. So I wonder if we get there, in the near future.
Yeah, so I think Eric said Plato, right? So Plato, the ESA mission, is going to observe for longer baselines in specific areas than TESS will. And it'll also, sort of like TESS, observe a larger number of A-type stars than Kepler did. So I think that's probably our best bet of really getting a better grip of this, 10 to 100 to a couple 100-day region of parameter space for A-type stars.
Cool, thanks.
Mm.
Eve?
Hi, Eve Lee, UC San Diego. I think you mentioned about the XUV luminosity with respect to the stellar type. So my understanding is that the ratio of XUV to bolometric goes down for higher mass stars, but the absolute value of the XUV luminosity is actually higher. So I think in terms of the effect on the planet, it actually might go the other way.
Gotcha.
But I guess my actual question, though, is so when you say small planets around A-type stars, what's the lower limit on the radius again?
Of the stars or the planets?
The planets.
So in the paper, I do go down to 1 Earth radius, but the 1 to 2 Earth radius bin is really crummy, and we don't really get good constraints. So so the radius that we get meaningful constraints down to is 2 Earth radii.
Right. And I asked this because I would be curious whether you see the same trends for the rocky planets, or whether that's whether you're more sensitive to the more probably gas envelope planets. Yeah.
Right now we're not super sensitive to rocky planets. Again, just because these are like big stars, small planets. But TESS is, fingers crossed, projected to keep going. And so, if you double your data set by a factor of 4, then you can maybe get those error bars down and start detecting those rocky planets. And then also, again, Plato is probably going to do a lot. It'll have a higher photometric precision, I think.
Right. Thank you.
Lauren?
Lauren Weiss. Thanks for this really awesome talk, Steve. So a couple of points, just to quickly respond to one of Eve's questions about what are your small planets. Even at 2 Earth radii, those planets should be predominantly rock by mass with just sort of a wee little bit of hydrogen helium on top. So to me, the lack of such planets interior to 10 days is this like striking success for core accretion theory of you can make planets where there's dust, you don't really make planets where there's not dust. And then also, I guess, for little planets, you're not doing a good job of migrating them inside that dust truncation radius, or dust sublimation radius. My question actually was a related question about the hot Jupiters. So a while ago, there was this toy theory of hot Jupiters maybe forming in situ around sun-like stars. And I know there's like some hot Jupiters around A-type stars. The KELT team surveys those. I'm sure you've looked at them.
Lauren, can you speed things up? Because we're.
Oh, sure. Yeah. Can you kill in situ formation for hot Jupiters based on the occurrence of such things around A-type stars?
Right. So I'd have to look back at the in situ hot Jupiter formation papers to like remember what the parameters that are relevant are. But I think, like you said, the fact that that we just don't have any dust less than 10 days around these stars probably inhibits the formation of the Jupiters there anyway. So yeah, I think it's hard. It would be hard to say anything definite, but you could probably make some inferences.
Okay, we got 2 more questions, but let's try and make them quick. Either way.
Well, just to highlight that, astrometry is going to be a good method for finding these longer period planets around A-stars. Both there's surveys at the VLTI and CHARA looking on them in special cases, and Gaia later. And then I just wanted, it came up in the last question, I thought there were a number of shorter period, hot Jupiters and A-stars not found with tests, so I didn't know how you incorporate that.
Yeah, so yeah, there are a decent number of hot Jupiters around A-stars that are pretty short orbital periods. So yeah, they probably, I would wager they probably didn't form there, but they get there somehow.
Great talk, Arturo Ceballos, UNLV. So about the last point about small planets being rarer than hot Jupiters. My question is, I don't know the timescale of formation. Like maybe since A-stars don't live that long compared to the smaller, less massive stars, could this be, rather than be an issue of migration, also be a part of the reason this is the case could be the timescale of formation of gas giants versus rocky planets?
Yeah, definitely could be. So yeah, my understanding is that we think the gas giants have to start forming pretty early to actually accumulate enough gas to get to where we are today. So yeah, and then again, we also know that these A-stars typically have like multi-planet giant outer planets from direct imaging. And so you combine that with the fact that the smaller planets might form later, and yeah, that could definitely mess up the entire situation for the small planets. So yeah, I think we'll have to wait for Plato to see if we do actually start seeing a lot of planets around these stars at longer orbital periods.
Okay, let's thank Steve again.